And our speaker today is Lin Jiayue. Sorry for the pronunciation, obviously. And she's a PhD from the Structural to Technical Engineering program, and she's working with Chiara Smiazzini. And today she will talk about seismic hazard and risk assessment in urban areas based on 3D physics-based ground shaking scenarios. So with this, Lin, the floor is yours.
Thank you, Chiara. Hello everyone, my name is Jiayue and I'm originally from China. I'm a PhD in deep art department and my supervisor is Professor Chiara Smiazzini. I'm going to give my topic today is about the seismic hazard and risk analysis based on 3D numerical simulations in urban area. And before starting, I really want to apologize that I was quite busy those days for the finalization of my PhD thesis, like a series of continuous deadlines. So I actually finished my slides like 15 minutes before this presentation, and I didn't really practice. But when I make these slides, I'm really thinking how can I deliver some knowledge, like people can take advantage, like for takeaway, like to respect the time of everybody. So I'm also curious and wondering what's the presentation I will give, but I hope you can get some knowledge for takeaway. And also me, I will wondering what my presentation will be. So let's start. So of course, like for every research, we have a motivation. And my research is in the earthquake field. During the past 20 years, if we see some data, the natural hazard has already increasing so much, especially within the 20 years. And among those natural hazards, the earthquake is one of the most serious one, causing the most number of the deaths. And also have a very large economic loss. And my research is about the risk analysis. So why risk analysis? As we can see from this figure, the role of this risk assessment is actually the foundation for the future reduction of the earthquake. So my research is about the seismic risk assessment. And for the background, like for the seismic risk assessment, well, we need to know the hazard map and the exposure model, combining with the vulnerability model, and then we can get the damage and the loss distributions along this chain. And my research is also focusing on the starting part about the hazards. Specifically, it's about the ground motion modeling and its associated uncertainties for the future seismic risk analysis. And for predicting the earthquake ground motions, the traditional method is the empirical ground motion prediction equations. It's based on the recordings, so it with some intrinsic limitations, such as it's poorly calibrated in the near source region, especially for the strong earthquakes, and it's not suitable to produce the spatial correlation and its cross correlation, and also it's too much generic size. Also, it's only provide the p-ground motion values. Simply say it's just because this method mainly based on the recordings, and the recordings are not always available anywhere. So it couldn't give a very region-specific and scenario-specific earthquake ground motions for the area that we interest. So this is the mainly limitations. And then we applied an advanced approach. We call it the 3D approach. This approach considering the seismic source, the propagation path, and also the local set conditions. And by using this method, we can take advantage of this method. Firstly, it gives us a more realistic description of the spatial variability of earthquake ground motion. And also because this method based on the physical parameters, so it gives us a chance to investigate what's the effect of those physical parameters. And also, like as I said before, since we can define our numerical model, so it can be suitable for the region and site-specific. Last but not least, it can provide us the full waveforms, which is potentially useful for the dynamic structure analysis. And for applying this approach, we've applied the computation code. We call it speed code. This is an open source coding. We can all visit and download and play with this code. This code was developed by the Polytechnical, the two different departments of Polytechnical. And this is the website. If you are interested, you are all welcome to play this code. And if you need some help, you can always message me, email me. I'm happy to help. So after the introduction of this background, my goal is to explore the physics-based numerical simulations to predict the earthquake ground motions for the future use of seismic risk analysis. And to give everybody a more clear flow about what I was doing, this is like some simply workflow. Firstly, we need to target our study area, and in my case, this is the Thessaloniki area. And then we generate the fault rupture realizations of this area. And then we apply the speed code and do the PBS simulations. After these simulations, we do some post-process for dealing with those data, and we can get the ground shaking scenarios. With these ground shaking scenarios, we can do the risk analysis at this area. And I would like to introduce a little bit the study area, why I choose the Thessaloniki area. So this is the overview of the study area with indication of the faults and the Thessaloniki. And the Thessaloniki is the second largest city in Greece, and it's the most economic center in Greece. Also, like the port in Thessaloniki is one of the most busy ports in Europe, so it's quite like an important area. Secondly, as you can see from this figure, it is located in a very high seismicity region, mainly associated with the two different fault systems, the Atamatas fault system and also the Macedonia fault system. Besides, like there is a very serious earthquake happened in Thessaloniki on 1978, and after this earthquake, researchers started to wondering like what happened in this area because it's really damaged, and because there are so many researchers do so many researches about this area, it gives us a chance to get a lot of detailed knowledge of this area, which is the necessary information that we need for the numerical simulations. So based on those factors, we decided to regard the Thessaloniki as our study area. And I will give a more detailed workflow about my research. So firstly, we need to collect some data, including the topography model, the geological model, and also some information about seismic in this area. And then we use this data as the input data to generate our numerical model using the Qubit software. And then we use the MATLAB coding to generate the earthquake ruptures and ruptures realization. And then after this preparation, as the configuration file for perform the speed, we run this 3D PDS method, and we get this result. And usually it's reliable up to 1.22 hertz because of the balance of the computation cost and also the level of details of our numerical model. So generally, it's reliable up to 1.22 hertz. But recently, also we have some research in our group can up to reliable up to 4 hertz, even 10 hertz. But in my case, it's reliable to 1.52 hertz. And since we get this reliable in a low frequency, and for the general use in the engineering, we need a broad frequency. So we apply the artificial neural network to generate the ground motion in high frequency. And here I give like a brief procedure about this ANN to BB method. Simply saying, it's like we trained a lot of data to build a relationship between the low frequency and high frequency. And since we have already got the low frequency from the speed method, and we apply this trained data set to generate, to predict the ground motions in high frequencies. So simply say this is the ANN to BB method. I hope it's clear for everybody. And after this one, we generate the ground motions for some scenarios around the Thessaloniki area. And then we perform the scenario-based seismic damage and risk analysis. So this is like a more detailed workflow of my research. So now I'm going to give an introduction of the 3D numerical model I built for Thessaloniki. This numerical model is built based on the previous numerical model developed by my supervisor on 2017, like 6 years before. And this is some information about the fault system we considered in this numerical model. This is the computation detail in this model. So what I updated based on the previous numerical model. Firstly, we consider two different basins. And Macedonia Basin is the basin that we ignored before. And also we give the we considering the different fault system, which is also have very potential use application for the future research. And also we give a more realistic velocity profile for the upcropping battle, and we generate a better mesh to provide a better discretization for the sediments. And also we give some sensitivity test in terms of the quality factor and also the linear, nonlinear factor something. And in a summary, the main updating is like two aspects. The first aspect is the 3D geological model. Like we make it more realistic. So those two figures is to show everyone like this is more realistic than before. And the second area is the velocity profile. In a summary, this is the profile of the 3D wave propagation model of my 3D numerical models. And I guess maybe some of them may be curious, like how you develop this model, why you decided this is your final model. So this is a list of the numerical simulations I performed in this research for validation purpose. And in total, we performed like 16 different numerical simulations, and we adding more features step by step to test how it affects our final results. So by doing this this process, we generate the binary numerical model. And when we develop this binary numerical model, we consider the different seismic source type, the different basins, and also the cropping, linear, nonlinear, like something. The purpose is just make our numerical model as realistic as possible. And then we do the validations with two real earthquake events. The first one is the event with magnitude 4.4. The second one is with magnitude 6.5. So let's go for the first validation case first. This is the basic information about this small earthquake happened on 2005. And in this earthquake, we have in total 9 recordings about this earthquake. And this is the comparison between our numerical simulations with the real recordings. The black line is the recordings and the red is our numerical simulation results. As we can see, like it has a general good agreement, at least between 1.5 Hz. And furthermore, we did another quantitative validation of the simulation for this same earthquake. This is the peak ground velocity map, and in terms of geometry mean horizontal component and the vertical component. And we calculate the goodness of each scores according to the criteria from the Anderson. And we compare 6 different earthquake ground motion intensity measures, including the peak ground motions and also the integral ground motions. And as we can see, general, like it shows fire to excellent scores for most stations. And then we did another validation with the bigger earthquake with magnitude 6.5. And we validated it by comparing with the empirical earthquake ground motion models. This is the figure for the comparison with ground motion models. And this ground motion model developed by Cozy on 2015. We refer it to as CEA15. And as we can see from this figure, it generally has a good agreement, especially in terms of the site A and site C, which is also the main soil we have in this area. And this is we investigate the spatial correlation of this area. And this is actually another big topic in terms of the spatial correlation, since I spent another 1 year to investigate this field. So I will not go for details to introduce this part because it takes another 20 minutes. So simply say, this figure, what you can take is the term of range. Range means like the distance, the correlation distance. Simply say, like for example here, the range equal to 64 means like this earthquake happened, and in this area within 64 kilometers, it correlated, like the ground motion correlated within 64 kilometers. And after of this range, we don't consider. So this is the spatial correlation. And why we consider the spatial correlation? Because the previous research has already proved that the spatial correlation has a huge, like obvious impacts on the risk analysis. And that's our goal, to give a realistic risk analysis. So we also investigate this part. And maybe some is still curiosity about the spatial correlation, so I give like a very general idea about this research, about spatial correlation. And we calculate the semi-varograms, like calculate the range, that is the term I mentioned before. And after those two validations, we measuring the variability of the ground motions, and we generate 60 different earthquake scenarios originating from 2 different fault systems with different magnitude. And this is the list and also the locations of those future hypothetical earthquake scenarios. This is the example, one of the example of the slip distribution, the rise time, rupture time of one scenario, like as an example. And we generate the ground motion maps. And then we compare it with the ground motion models again to as a further validation, like a verification of our research, of our method. And here, what I can deliver to everyone is this frequency histogram and the best fitting log normal distribution in the Thessaloniki city area. And by doing this analysis, we know that the earthquake scenario from Macedonia Basin is more dangerous than the one from Atamatas, even though Atamatas is actually near the Thessaloniki. So this is like something the city can use, can consider for reduce the damage of the earthquake. After this one, we did the seismic-based risk assessment using the OpenQuake software. So now we have the hazard map from the speed. And we're combining the updating fragility and vulnerability model, and then we can get the damage and loss distribution of this area. And this is like some examples of the risk of the damage distributions from 3D PBIs comparing with some other ground motion models, and you can see it also have a general agreement. But remember, like we give more details that the traditional method cannot give. This is the advantage of this method.
The damage is a numerical value, or it's in economic value?
This is the economic.
So
No. We should mean the damage distribution over the time.
But vulnerability is referred to some type of structure or some type of exposed value.
Do you mean this figure? This figure is the fragility model of this type of buildings. And this is the loss ratio of this type of buildings. And by
So you have also distribution of the buildings in the area.
Yeah, I have the distribution of that is the exposure model of Thessaloniki area. We will apply that one, we combine that one, and also the fragility vulnerability model, and then we perform the damage distribution analysis.
So what are those numbers, like 8606? The numbers in the pie charts.
This is the. Sorry, I didn't give so many details about the exposure model you mentioned. This number is the number of buildings suffered the damage, and I'm sorry, I forgot to give the indications. The red means the complete building damage state, and the green is the slight damage. As you can see from here, different colors.
So the number of buildings and the percentage.
Yeah. The percentage over the total building. I'm sorry, I forgot to give more details in this part. Okay, so now it's almost finished of my presentation, and since it's actually not a very scientific, very formal conference to deliver my research. So here, actually, I put these slides for my personal feelings. Maybe when people mentioned about the earthquake, many people expected to some pictures about the damaged structure. So here I will give you one. So this is the damage structures in Turkey, like recently happened. But we cannot regarding like the disaster as numbers or pictures because it's actually related to our life. And sometimes we cannot do something to the area or the perceived reality. But at least, like if we can do nothing, at least when we heard something, we give like we deliver our wish energy to the place. Like so, this is my personal side. I'm sorry, this is not so scientific, but I take advantage of this chance to deliver this to everybody. When we heard something, we cross finger to the person of that area. Okay, now it's finished of our presentation, and I'm really grateful for having me here. And my research is funded by the Horizon 2020 Mercury Actions. And also, I was doing my segment in Aristotle University, which is actually located in Thessaloniki. So when I do this research, actually, I have a different connections with Thessaloniki because I really stay there. I know like where has some good shops, like a good cafeteria. So I'm really grateful for this project, like bringing so many good experiences, and I'm also appreciate like the life experiences, the PhD life in Polytechnical. So finish. Thank you.